Hello, Cappuccino. Here is a video trying to explain what we were doing the other day on Tuesday, where we were trying to linearize an exponential function and a power function. So why are we learning this? All right, here we go. So notice on the screen here, I have 4 different curves. And let's say I wanted you to figure out the equation of each of these curves. Well, what kind of function would you use? Would this maybe be a quadratic, something with an x squared? Or is it an exponential where it's some number raised to the x value, like 2 to the x? How can you figure out which one is which? So being able to linearize a function helps us determine what type of function is, what type of function you have. So if you're given raw data and you plot it and it somewhat resembles one of these shapes, then you want to know, well, what kind of function should I be using to model this data? So let me show you what we've got here. I had the red line is a quadratic, x squared. That's also called a power function. When x is raised to a power, that we call that a power function. The next one is an exponential function, the blue one, 2 to the x. So when x is in the exponent, we call that an exponential function. The next one is also exponential, that's the green one, and that's e to the x. We use e a lot, especially in the biological sciences. And then the last one is a cubic, also known as a power function, and x to the third, and that's the purple one. Okay, so if you had data that roughly followed one of these curves, how would you know which one it was? Well, you could, sort of just guess and check, but there is a precise way of figuring it out. So that's why we linearize. So I am going to show you what happens when you take different functions and you try and linearize them like we did in our assignment in class. Okay, so the first one we're going to look at is here we have a quadratic. So the red line is y equals x squared. And then I created the table for y equals x squared. So if x is 1 through 6, then y would be x, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. And you can see my little green dots on my red curve. Okay, so those are the points that are creating that curve. Now, if I do a semi-log graph, where I just take the logarithm of the y values. So you can see that in the next table here. So I kept my x values the same. And then I changed my y values to the natural log of that y value. And I could have done any base. I could have done base 10. I could have done log 1. But I decided to just go with natural log. Okay, so I did natural log of 1, 4, 9, 16, 25, and 36. And here's what we get. So kind of interesting, but it's not a straight line. So that doesn't seem like we are linearizing anything. Okay, so I'm going to go ahead and turn that one back off. Well, what if I take the log of both? So this would be a log-log graph. Okay, so the first one here, this blue one, that's a semi-log because I only took the logarithm of the y values. But now for the next one, I am going to go ahead and do a log-log. So I took the log of the x values and I take the log of the y values, and look what happens. Lo and behold, the new points make a straight line. They make a straight line. Okay, so something else that's even more extraordinary is if I look at the slope of this line, if I find the slope of this line, and I can do that by taking rise over run. So my change in y over change in x, my change in y is 1.38. So I'm going to go down here and I'm going to put that in. What did I say? 1.386. 1.386 divided by change in x, 0.693. 0.693. Look what I get. I get 2. I got the number 2. Okay, so what was the original function here? Oh yeah, y equals x squared. Hey, where have I seen that 2 before? It was the exponent. Okay, so notice again, just to recap, when I did the semi-log, not too interesting, did not linearize my function, but when I did log-log, then I ended up with a straight line. All right, let's go to the next one. So looking at an exponential function, so here I have y equals e to the x. And you can see here is my points on that graph. So I just substituted in 1 for the x, and then 2 for the x, 3 for the x. Okay, and you can see the purple dots falling on that function. This is an exponential function because x is in the exponent. And then I went ahead and I made a semi-log and a log-log table. Okay, so let's go ahead and look at the semi-log first. And notice what happens. They are all lined up, all in a row. Okay, what happens if I do log-log? So let's turn that off. So that linearized it. Okay, doing a semi-log on an exponential function gives you a straight line. What if I do log-log? Oh, that does not give me a straight line. Okay, that in fact actually matches the original function. That's bizarre. Okay, but there it is. So if you have an exponential function, if you do a semi-log, it will linearize it. But if you do a log-log, it does not linearize it. So if we went back to our why do we linearize, if you have data and you don't know what type of function you should be modeling it with, what you can do is you can do a semi-log graph, see if it makes a straight line. If it does, the semi-log graph makes it a straight line, then you know it's an exponential function like e to the x. But if a semi-log table or a graph does not give you a straight line, then try a log-log. If it's log-log, then it's a power function like y equals x squared. And we saw that when you do the log-log, the slope of that line, see my red points here, the slope of that red line ends up being the same as the exponent. Now, is that true? Okay, let's prove it. Let's do another one. What if we have a cubic? So here I have a cubic. So this is a power function, not an exponential function. And I've plotted it, plus here's the values. You can see they're falling on the graph. So when I do the first table here is going to be a semi-log. So I just took the log of the y values. So since this is a power rule, we should be guessing this is not going to make a straight line. Should not make a straight line. Only exponential functions, when you do a semi-log, make a straight line. Oh, yep, no straight line there. Okay, so not very handy. But if we do a log-log, this should make a straight line. Let's see if it does. Aha, it did. That is making a straight line. Okay, so what is the slope? Okay, so here's 0, 0. The next point is we want to do our rise over run. So from 0, 0 to the second point, change in y over change in x, it's just going to be 2.079. So let me write that down. 2.079 divided by the x value, 0.693. 0.693. And lo and behold, what do we get? Oh, it's the power. What do you know? So you can use these, a log-log graph. If you have data and you're trying to figure out, is it a power rule or is it exponential? You can do the semi-log and the log-log to determine whether it's a power rule like power rule like x squared, x cubed, x to the fourth, x to the fifth, x to the sixth. You can do that. Do a log-log, and the slope of the line is going to be the power on your power rule. All right, so this is why we like this linearization. It tells us the difference. Again, going back to which graph is which. If we didn't know what those functions were, how could we figure it out? If we have points, if we have data that follows one of these curves, we can put it into a table and we can do a log-log and see if it straightens it out. If a log-log straightens it out, it's a power rule. If a semi-log straightens it out, then it's exponential. And so that helps us figure out what's going on. Now, if neither of those work, then it's neither a power rule nor an exponential. And so then you probably want to look and see if it's sinusoidal. Alrighty, so that is the why do we do this part of the video. And now we will go to our notes and we will write down what we just figured out.